Okay, so probably we could start already. So today we have an interesting lineup. Two of my colleagues, Gauthier and Christian, from the welding group here in the robotics department at Fraunhofer IPA, will be presenting their latest developments.
Hello, everyone. Sorry.
They have been working on. Actually, Christian had presented back in August 2020, but they have quite some interesting updates now, and they have also a really cool video. So Christian and now his colleague Gauthier will be presenting together. And also we have today, after their presentation, Sebastian Jahr from MoveIt. Sebastian, are you an intern at MoveIt or?
Yeah, I've started as an intern last winter, and during this internship, I developed the hybrid planning architecture, and now I'm a working student at PickNik.
Cool.
Yeah. So just
Okay.
a part-time job.
Yeah. So yeah, Sebastian will be presenting his work, what he did with hybrid planning. Now that we are seeing so many interesting applications in ROS-I, similar to scan and plan, I'm sure it's a good time to talk about hybrid planning. So yeah, after these talks, if there are any open issues, if any of you have any issues to talk about, we should have enough time for that as well.
Thanks for
so the
having
floor
me.
is, yeah. So the floor is yours, Gauthier and Christian. You can divide your presentation as you have decided. Please go ahead.
Yeah, I can share my screen. I hope it's visible to you.
Yeah, it is.
Okay, nice. So yeah, say hello everyone, and thanks for the invitation, Harsh. So me and my colleague Gauthier will present some of our progress or latest work in using ROS for welding, and the results of of our biggest projects, which have been around for the last couple of months or the last years nearly. So yeah, I will start with giving a short introduction about our progress and our state of our motion planning toolchain for this robotic welding problem. And then we will show two example application scenarios where we applied ROS for welding. And yeah, so we'll just get into the introduction part. If I miss something or if you have any comments, feel free to interrupt me or comment me. Yeah, so where did we come from? So our group is focusing on Cartesian processes in robot manufacturing. And when I started, I think in the end of 2019, we were like heavy into this offline programming systems for welding. And yeah, so it wasn't based on ROS, and it was mainly our own development, and we were thinking of how to make use of already existing packages and already existing work of other research institutes. So we decided to switch to ROS, or to migrate our toolchain to ROS. Yeah, maybe the first part is just like some similar projects we discovered in the ROS industrial world. I think if there are also some great tools from the Southwest Research Institute for, I don't know, sanding, for example, or painting, polishing, and so on. And the Tesseract framework. But since our main focus is more on arc welding and recently also on high precision printing, for example, of sensors and similar things, we have a slightly different background, I think. And yeah, we also discovered this ROS additive manufacturing framework of the Institute MoveIt2. but which is more focusing on generative processes and not which are have slightly different constraints than our welding toolchain. Yeah, I'm sure there are also like other ROS-based pipelines for Cartesian process in the field of inspection or quality control, but yeah, I haven't been aware of when I prepared the slides. So yeah, on the next slide, I will just give an overview of our toolchain and give the relation or connection to the ROS industrial community. Just maybe discover some links or connections between our research. So when we want to weld two or multiple parts together, the first we start our toolchain with determining the task or to finding the weld seams, or yeah, that could be either depending on if we are like in the online world, it could be based on point clouds in 3D data, or if we coming from the offline world, it's more like a CAD-based task recognition problem or like a CAD-to-path problem. So this is, I think, quite related to other ROS industrial tools as Gauthier or Gauthier, or yeah, I'm sure there are many others, but we focus on the weld seams instead of a surface-based detection. And the next step in our toolchain for motion planning is to have like a high-level planning stage where we combine and order the detected tasks and define VR motions and approach and retract positions for the welding gun, and also we might have to include additional tasks for scanning or cleaning or removing of slack or some other stuff which could appear. Yeah, this leads us to the low-level process constraint path planning, where we have to generate trajectories for the detected tasks by considering the process constraints, and also have constraints regarding the speed and for example the wire feed and other things we have to consider, which is where we have quite interesting followed the project for adding constraint planning opportunities to the MoveIt framework. And yeah, and then the next step in our motion planning toolchain for welding is to adapt to tolerances or deviations in the initially recognized tasks. For example, because of assembly deviations in the assembly, or changing local positions of the next workpiece and so on. So this could be either done in an online way or in an offline way where it's more connected to path optimization and not the classical seam tracking problem. But I think Gauthier will go into detail in the next couple of slides. And then the final step after the seam is placed successfully is some quality inspection and monitoring, where we haven't been focused that much. So, for example, you might automatically want to determine if the weld seam quality is high enough, or if you produced bad workpieces, or maybe you need to post-process the workpiece, for example, by removing slack on top of the weld seams, or you may want to collect data to learn from for the next workpieces, or to gather knowledge of the process. I think one problem where we have which we have solved in our or which we discovered in our toolchain. Is that ROS is not that not that much meant to include tool changers or dynamically changing a robot layout. So we will show later how we solved this issue. So far so good. I will jump to the next slide. So to put these different parts of our toolchain together, and what we actually have done with our toolchain is we had to connect multiple or several individual components and had to bridge the gap between, for example, manipulation and in MoveIt or in ROS with CAD/CAM tools and so on. So in general, for the manipulation part of our toolchain, we were heavily based on MoveIt and the MoveIt task constructor and other components of MoveIt. But since I think MoveIt is quite focusing on free space motions and just recently added some things like the Pilz Industrial Motion Planner, we had to adapt, for example, the MoveIt. We adapted, for example, the MoveIt task constructor to be able to used for welding or multi-layer welding as well. On the other hand, if you look on the CAD/CAM world, most of the components there are like closed source, expensive tools. So we developed a package to integrate some open cascade opportunities into ROS to recognize tasks and describe tasks in workpieces. And the third point, to integrate the welding process knowledge, we had a problem that there's not that much a common design to describe process or manufacturing processes in ROS or in ROS Industrial. So we try to design our own standardization of a welding process. And last but not least, to integrate the laser profile scanners, which are usually used for welding or for seam tracking and welding, we developed a calibration procedure and solved some issues for ensuring the high quality also during the welding process, and such that the sensor is also seeing something when actually welding at the same time. So our software toolchain is mainly focusing on trying to bridge these gaps of the different parts I just presented, which we recently started to call kind of process it, with the idea to provide an extension of MoveIt and a link to process-related components, and for especially focusing on welding and other Cartesian processes in ROS. And last but not least, it's also always important to have some nice user experience or to have some nice videos. So we try to extend the external control UR cap to be able to call our components from the UR teach panel in this case, since we were heavily focusing on universal robots. And so the next step will be to try to get all these components more independent of our specific scenarios, and maybe try to open source something in the next time. So that was more the theory. So I will present the first project, publicly funded project, which we had in the last year. So there our goal was to make use of a laser profile sensor to automatically detect and plan weld seams without any prior knowledge from CAD files or any more complex stuff, such that it can be really used on the shop floor level, and with the goal to avoid this tedious and time-consuming fine-tuning of robots, which you have usually to do when you export programs from the offline programming system, or if you program welding seams online with the teach panel. So this video is more like an amateur video. It's not a final project video, but you can get the idea. So the idea is that the worker can roughly program the poses or the start poses of the weld seam to the workpiece without any fine-tuning or really perfect programming. And then with the laser line, which is coming from the sensor, which is not visible on the video, but which you can like think of pointing on the weld seam. The weld seam is automatically detected in the point cloud, and by using the user input for tool position or tool orientation and speed, the welding is done automatically. And it's also possible to use it for existing programs, or for slightly different positions of the weld seams and so on. So yeah, we had to. So basically, the tool chain is our online part of the tool chain is called from the UR teach panel, and ROS is running in the back and in the background and performing the computation for generating the trajectories. Yeah, so I think on the next slide, Gauthier will have the word.
So yeah, our second big project was industrial funded project. Here the application is multi-layer welding of columns on construction sites. And for this application, we developed hardware. So you can see on the left the kind of workpiece that we want to weld. So basically huge columns put in one of the top of each other, and you have a huge gap to fill with several welding seams. So we use a Fraunhofer welding source, and we developed a movable platform because we didn't focus on autonomous motion of the platform, with a welding torch with a laser scanner, and also a tool changing station, because for this multi-layer welding application you need to clean the weld seams after each pass. So yeah, the challenge is basically to achieve a good quality of the seams layers after layers. So we need to position the welding gun quite precisely. So the positioning of the robot with respect to the column is important. And also we did a lot of experimental studies for finding the welding parameters.
Gauthier, can you just come closer to the mic, probably?
Oh, yep, I can. Maybe like this. Next slide, please. So we have a final video showing the results. So basically, it's a adaptive offline programming toolchain that we integrated in ROS. So we integrate the cell together with the workpiece, and we generate a description of the weld seam with linear segments. And using this description, we first plan a scanning path with appropriate offsets to get a good quality of point clouds. The part is measured in simulation and in the reality, so we get a virtual point cloud and a real point cloud, and then we match them together to find the real position of the welding joint. So you can see here the quality of the point clouds that we get. so real and simulated. And so once we get this transformation, we move the workpiece in the simulation. You can see here. And the task description that is also moved together with the workpiece. So finally, we use, as said, the position of the gun is determined experimentally. So the welding angle, the stick outs are all stored in the software for this particular workpiece and fitted with the localization toolchain. And here you can see that this approach allows to achieve quite high welding quality over, I think it was 14 or 15 welding seams here. Maybe you can skip to the tool changing part.
No.
Yeah, so we also use the MoveIt task constructor to handle tool changing. So to use the collision avoidance to attach, detach the tool, and then so using this tool changer, we can remove slag after each pass. Yeah, and finally, I think there is a little picture of the final result for the welding, which is a pretty good quality. So then I have some slides about the technical developments. Some are quite prototypic, other are more ready. So the advantages that we found using the MoveIt task constructor for our high-level planning is that we can handle collision checking with different tools. So we can deactivate, reactivate collision checking between the welding gun and the column and the slag removal tool also. And we can also generate all the trajectories for the different subtasks. And yeah, in the longer term, optimize the cost over the whole task sequence. So you can run the video, I think. Just, I mean, it's nothing impressive, but just to show that we implemented some subtasks to pick the tool, deactivate collision between the robot and the tool, then reactivate it and ensure that all the motion are then collision free with 1PL. So yeah, one of the implementation is this kind of hacked usage of MoveIt task constructor to manage tool changing, and the other one is the definition of stages for Cartesian motion. So we defined generic Cartesian stages and also stages specific to welding, scanning, and cleaning of weld seams. And yeah, the things that we plan to further develop is to provide the end user a possibility to program a list of subtasks in a user-friendly way. Currently, it's coded with YAML files and those specific stages. And we also need for welding to integrate a workpiece positioner and the path planning of the robot with the workpiece positioner. Yep, next slide. The second development, and there are also others actually, but the focus that we want to give today is the on-project constraint planning. So we had a colleague that was working with ONPL and commercial OLP software in the past, but there was some limitations. So this is also one of the reasons we moved to MoveIt and ROS. And so based on the result of the Google Summer of Code of 2020 about integrating web constraint planning in MoveIt, we try to apply this to welding. So the idea is that we can plan welding path that respect the process constraints in an optimal way and at the same time avoid collisions, and also find the best inverse kinematic solution for the different welding tasks. So one of the implementation we made is to also define constraints based on linear system of equations So we can plan position constraints for lines and for circular path. But this is still also prototypic. And we added some tutorial steps for position and orientation constraints on a path. So I think you can show the video. So just in this project, we also implemented, tested some functionalities. So you can see this task description that we have again. And so we used it to avoid collision between the robot and this erection piece that you can see here. But we still need to implement the cost constraint. So we can also use it for collision-free path planning between welding seams, and we can use it to avoid collision at start position for welding. And finally, here you see the circular constraint. It's a bit fast. And here a second solution to avoid collision between the two seams. Yeah. So the roadmap here, we wonder how to blend segment, because for welding we need to be able to weld continuously linear plus circular segments, and right now with OnePL and MoveIt structure it's not possible. We are also pretty interested in getting deeper into the Cartesian trajectory message, or what the Forschungszentrum Informatik and Universal Robot are working on about Cartesian trajectories. Also, we are interested in maybe testing combination of OMPL and Trajet to have better performances, because the results that I show here, it's several, or up to some minutes of computation, so not optimal. And yeah, so our idea is to define the constraints for the path directly from the CAD data, from the step file. And yeah, we need to define the cost function specific to the welding process so that the angles for welding are respected, or at least kept optimal. Okay, and the last slide. So we wanted to start a discussion. I don't know how we want to do it, if we first do the two presentation and then we go for the discussion, or we can already discuss now.
Yeah, probably I can just shortly ask around if anyone has any questions specific to Christian's and Gauthier's presentation. Okay, seems not to be the case. Then thanks, Christian and Gauthier.
I can just give the 3 points and then we can go to
it later. Sorry, I thought you already did that. Sorry.
No, but so yeah, the discussion, I think in the first slide we showed that there are many, like several pipelines for such Cartesian processes, and we would be interested in discussing with other developers. We are already in contact with some French institutes to think about finding some synergies. We are also interested in maybe defining some standard welding message and working on the Cartesian standard messages. And yeah, maybe a long-term idea, but probably everyone already had some time in mind to have a standard ROS industrial package for Cartesian process. But that's probably a bigger question. Yeah, thanks for your attention.
All right. Now, thanks, Christian and Gauthier, for the presentation. Seems to be quite some progress from Christian's previous presentation, what he did in August. And so I think, as Gauthier mentioned, their group is already looking to open source at least parts of the work they have done. Currently, Nadia is working with them to talk about best practices and things like that. But yeah, as Gauthier said, probably it might be a good time. I don't know if it makes sense to come up with some kind of rep for some messages, let's say, for or interfaces for process planning, these kind of things. And yeah, also to have some kind of let's say guidelines or best practices to have these kind of complex pipelines. We already have some really good examples from Godel and the sanding application what's really developed, and now with ProcessIt. So yeah, I can imagine that there might be many more such contributions. So probably now is a good time to start some discussion on these topics. Yeah, so does anyone have questions to Gauthier, Christian? All right, then Sebastian, I think you can go ahead with your presentation.
Okay. Can you hear me?
Yes.
Okay, perfect. Then as I mentioned before, thanks for having me. My name is Sebastian Jahr, and last winter I did an internship at PickNik Robotics. And during this internship, I developed a hybrid planning architecture for MoveIt2. And I continue working for PickNik now as a part-time student, working student, and try to move the hybrid planning architecture now as a main feature of MoveIt2. And in this presentation, I want to give you a quick overview about what is hybrid planning, what is the hybrid planning architecture that I designed for MoveIt2, and what is the current state of the work and the future plans for it. If you have any questions, feel free to interrupt me anytime. And first of all, I will start with a quick introduction to MoveIt, although it seems like most of you already know it. So what is MoveIt? MoveIt is and this sentence is directly copied from the website. So it's basically an easy-to-use open source robotics manipulation platform for developing commercial applications, prototyping designs, and benchmarking algorithms. So it's a whole framework built on top of ROS, dedicated to motion planning. And besides the pure motion planning functionality, there are also many other features, like, for example, there's a pipeline available to include 3D perception data into your motion planning problem and stuff like that. If you're interested in that, you can check out the website. So, but I think it's quite interesting to know that MoveIt is just this huge framework with more than simply the possibility to use motion planners. And at its core, so the motion planning pipeline can be seen somehow like this. So we have some kind of motion plan request, and we can adapt this request with several motion planning adapters. There's a little copy and paste error. The time parameterization is should only apply for the post motion planning post processing. But basically, we have some pre-processing of the request. We have at the core some kind of motion planner. There are different motion planners available, and you can easily add your own motion planner by writing a C++ plugin. And after the motion planner generates some kind of motion plan, we can post process this motion plan for example, with time parametrization and adding a velocity profile, and afterwards the pipeline returns a motion plan, and this motion plan can then, for example, be executed by a ROS control-based controller. And the second kind of main component of MoveIt is this planning scene monitor, which is used to monitor the state of the environment and the planning scene and the robot itself, and it's basically the source of the planning scene for the motion planning pipeline. Just to give you a quick heads up, what's the core of MoveIt. And for this architecture, I developed I extended it to make hybrid planning available. So first of all, what is hybrid planning? In this slide you can see a little example of different paradigms of motion planning. It's from the demo video of a paper published in 2018 by a working group of the Max Planck Institute for Autonomous Motion in Tübingen. And we kind of see three different motion planning paradigms applied here. So on the left, we have, we can see, do you see my, my mouse on the slide?
Yes.
Okay, perfect. Yeah, on the left, you can see the most simple motion planning paradigm, and probably the most popular. They call it one-shot planning, or you could also call it sense plan act. So we kind of sense the planning scene, then run a planner, and afterwards execute the generated trajectory. This is also what MoveIt without any controllers would probably do. And if the planning scene changes after we ran the planner, we have no possibility to adapt our solution to this change of the planning scene. And in this simple scenario, this isn't an issue because we can simply push aside the collision object. But yeah, of course, you're aware that this is a huge issue that we run into the collision object. The usual approach to kind of handle this problem is to execute your motion plan solution with some kind of controller. But this controller, or they call it local planner, is only capable of not running into the collision object, but we get stuck in this local minimum. So we're not able to steer around the collision object. But we have to wait till the collision object is removed once again. And to overcome this issue, they call it continuous motion planning, but you could also call it planning and control or hybrid planning. We combine a global motion planner with a local motion planner. And with that, we're able to adapt our global motion plan to changes of the planning scene and use the local planner to keep the immediate path of the robot clear. For example, if the collision object would appear faster, the local planner would first make the robot stop and then trigger the global planner to steer around the collision object. In a more abstract way, you can see this on this slide. This is the current state of MoveIt. We have some kind of global planner. We get this planning scene snapshot as a static planning scene, and then we apply our global solution with some kind of motion controller, but we're not capable of handling dynamic planning scenes. And to overcome this problem, as I mentioned before, is to use this hybrid planning paradigm. So we combine our local and our global motion planner and have kind of two different closed loops to react to changes in the environment. So the local planner can handle local immediate changes of the planning scene, and the global planner can be used to, for example, prevent the local planner from running into a local minimum or get stuck there. You could also say that the local planner could be used to adapt the global trajectory to local conditions. So referring to the previous presentation, when you try to weld something, you could use the global planner to kind of plan the trajectory of the whole path where you want to weld. But the local planner could be used to keep a certain distance of from the surface and to adapt this global solution to, for example, unevenness on the surface to weld, and to keep the same distance between the tool and the surface we want to weld. Yeah, this slide shows the difference between global and local motion planning. So global planning is basically what MoveIt currently does. We are capable of planning around complex obstacles. We can use it to avoid getting stuck in local minimum, and it's probably complete. So we will find a solution if it exists. Although this comes at the cost of much lower computation time, and the global planner is usually not real-time safe or deterministic. And our local planner, on the other side, is fast and reactive and deterministic, but can get stuck in a local minimum and might not be as capable as the global planner to make collision safety guarantees for a large trajectory. The advantages of combining both are summed up in this slide. So when we can simultaneously plan globally and locally, we can run both planners at different planning speeds, and therefore, for example, the local planner can be much more reactive to changes than the global planner. We could use the local planner to include force-based planning, for example, and yeah, example applications would be the usual applications for motion planning. So human-robot collaboration, the local planner could be used to kind of guarantee us that we don't run into the human when he or she does some unexpected motions. We could use it to paint a wall with the global planner, for example, planning the global trajectory, and the local planner, as in the welding example, adapts this global solution to local unevenness or uncertainty. Yeah, this is basically what hybrid planning is, and I've developed an architecture for MoveIt2 to enable the capability of hybrid planning. The main concept is that we have a third component additionally to the global planner and the local planner, the so-called hybrid planning manager, and this makes the whole architecture much more reactive and event discrete. So the hybrid planning manager provides an interface for the user for the hybrid planning problem, and it's kind of the brain of the architecture and determines how we react to certain events, or in which order we run our global or local planner, depending on the scenario where we want to use the architecture. Same as MoveIt itself, one main goal for the design was to make the architecture as customizable as possible. So basically, it's all up to the user what this hybrid planner actually does and which algorithms he or she wants to use. A more detailed view on the architecture can be seen here. So first of all these components of the architecture are ROS-2 component nodes. A component node in ROS-2 is kind of the same as nodelets in ROS-1. So we can use component nodes to reduce messaging overhead by running different multiple ROS nodes in a single process and use, for example, inter-process communication to let the nodes communicate with each other. The hybrid planning manager has an interface for the user. The interface for the user for this whole architecture is some kind of ROS action interface, and the components communicate also over ROS communication interfaces with each other. And the actual behavior of the hybrid planning manager, and therefore the whole architecture, is within this planning logic plugin. I will explain in the next slide what this planning logic actually is. The global planner component also offers ROS-based communication interfaces to communicate with the other components, and utilizes the usual, the normal MoveIt planning pipeline for the global planning. So basically, every motion planner that is currently available for MoveIt can be used as a global planner in this hybrid planning architecture. The local planner is a little bit more complex because it consists of two different plugins. We first have the trajectory operator plugin, which has the task to manage the local planner's internal reference trajectory, which is basically the global solution that the local planner tries to execute. And the trajectory operator plugin, on the one hand, updates this this reference trajectory. For example, in the first, if we get an initial global motion plan, the update of the reference trajectory is, of course, very simple because we just use this global this initial solution as reference trajectory. But the moment we get an updated global trajectory, we have to consider several things. For example, at which part do we dump the old global solution, and how can we go from the previous global solution into the new global solution. So basically, trajectory planning. Planning is handled by the trajectory operator plugin, and each loop run of the local planner, the trajectory operator plugin determines the local planning problem. For example, a very simple local planning problem would be to just check at which point in the global trajectory we currently are, and then forward the next waypoint to the solver plugin, which implements the local planner algorithm that is used to solve the local planning problem. For example, there are different possibilities which algorithms you could use. For example, you could simply use some kind of IK solver as a very basic local planner. I talked about the planning logic, which determines the behavior of the whole architecture, and an example can be seen here. So basically, the whole hybrid planner has some kind of internal state machine, which can be seen as the local as the hybrid planning logic, and we kind of start in this await planning request state. And the moment we get this hybrid planning request, this is an example for a logic. You could do anything basically. You could also implement a totally different logic to operate your hybrid planner. But in this example, we just run the global planner once we receive this hybrid planning request in order to generate some initial global planning solution. And if the global planner is not able to find a valid solution, we just report failure to the user and go back into this waiting state. Otherwise, we forward the global response to the local planner and let the local planner execute this global trajectory without the option, for example, to replan an invalidated global trajectory. you could, of course, this planning logic gets more complex the more functionality you want from your hybrid planning architecture. For example, if we want to include replanning, we would need to add more states to this planning logic. Yeah, this is basically what I explained about the local planner plugins. The trajectory operator plugin is used to manage the reference trajectory. Also, for these two plugins, it's possible for the user to implement its own algorithm how to do that. The architecture basically defines the interfaces necessary to kind of plug in your algorithm into the whole hybrid planning architecture, but it's up to you what to actually do with the architecture itself. Just a quick note why we decided to use ROS-2, and yeah, basically, I think 2019, the first version of MoveIt2, which is MoveIt for ROS-2, was released, and ROS-2 offers various advantages over ROS-1. First of all, we don't have a ROS core anymore, so we kind of have a decentralized system. So, for example, with this hybrid planning architecture, in case some of the components experiences a failure, we can just isolate the component and can only restart one part of the architecture without the need to shut down the whole architecture and the need to rebuild the whole thing. Secondly, ROS-2, and this is a dangerous sentence, but ROS-2 is real-time capable. As you might know, ROS-2 is based on a DDS-like middleware and doesn't use this custom communication protocols anymore that ROS-1 uses. And some of these middlewares that ROS-2 supports are real-time capable. Therefore, if you kind of use the right setup and if you make your ROS-2 nodes real-time capable, it is possible to achieve a low latency control loop with safety guarantees with ROS-2, which is not possible with ROS-1. Another advantage is that components are now a main feature of ROS itself and not this node package anymore. So we have more efficient communication between different parts of our architecture. And another feature that was introduced with ROS-1 are lifecycle nodes, which are basically ROS nodes with an inherent state machine. So we have the possibility to have kind of managed nodes at runtime that have different states, for example, the configuration state or the running state or an error state, and that out of the box without further need to program that yourself. The architecture is implemented right now, and I've created some proof of concepts demo I'd like to show you quickly because I see that the time is nearly over. So the first demo I've created is this Sense Plan Act demo, which shows which uses the hybrid planning architecture just to act the same way as MoveIt1 does. We have a set of 3 different plugins. We use as a planner logic a simple plugin that basically is just a single plan execution logic, similar to the one I've showed you before. The trajectory operator plugin just forwards the global solution point-wise to the local solver, and the local solver just forwards this point to some kind of trajectory controller. And as you can see, we run into our collision object and don't have any benefits from this hybrid planning architecture. And this can very simply be changed by exchanging just one of the plugins of the architecture. Now we use as a local solver plugin this so-called stop before collision solver, which basically gets a local trajectory and checks for collision objects within this local trajectory. And in case this local trajectory, so this part of the global trajectory, we want to execute is invalidated by some kind of collision object, the local solver just keeps the current position. If I would remove this collision object, the local solver would continue to move to the desired goal position. But even in this example, we don't utilize the full capabilities of the architecture, because of course we want to replan our trajectory, and this can be done by altering the use planner logic, and we use now a different planner logic plugin, the so-called replan invalidated trajectory plugin, and the local solver plugin sends an event to the hybrid planning manager the moment it realizes that that there's a new collision object within the desired local trajectory, and then the hybrid planning manager just re-triggers the global planner, and as you can see here, the global planner then creates a new trajectory to the desired goal position, and we're capable to adapt our global solution at runtime to the dynamic planning scene. Yeah. This is the more detailed part of this. I think I will skip this because of the time. But if you have further question, I can show you this later. Yeah, future work. The current state of the architecture is that it's fully implemented, and currently lives on a feature branch of MoveIt2. We want to merge it into the main branch this month, but we need to add for example, unit tests first before we want to do that, to keep the code quality up. Then currently the architecture is just that, an architecture, and it offers the possibilities to do very cool stuff, but yet there aren't much sophisticated local planning algorithms. So one intermediate step would be to add more sophisticated local planning algorithms. For example, we're thinking about using, for example, BioIK or MoveIt Servo as a local planner in combination with the global planner, or as you mentioned in the previous talk, you could use DredgeUp, for example, as a local planner, and OMPL as a global planner. That would also be possible with this architecture. The next step is, of course, to create some kind of hardware demo and tutorials. Yeah, I'm working remotely from my shared flat in Karlsruhe. So sadly, I don't have a robotic arm here, but yeah, we try to fix that, and with the increasing number of vaccinated people in the United States, we hopefully get a hardware demo running within the next 2 or 3 months. As kind of the first part of my part-time job at PickNik, I created an interface with ROS-2 control. So now the local planner sends motion commands to a ROS-2 controller, and therefore the integration with real hardware should be relatively straightforward. Then we want to use lifecycle component nodes in ROS-2. So ROS-2 supports lifecycle nodes and component nodes, but the next release of ROS-2 supports lifecycle component nodes. So we hope to change that within the architecture with the release of Galactic, and a more distant future work would be, for example, to add more complex global planners, for example, an anytime planner as a global planner. An anytime planner is a planner that creates an initial global solution and iteratively optimizes it at runtime. So this would enable the architecture to be more capable of being used as for online motion planning. Yeah, So thanks a lot for your attention, and yeah, I'd be happy to answer any questions you have.
Thanks, Sebastian. That was a very, very impressive presentation. Nice to see the progress you have done in the last few months.
Thanks.
And really glad to see that it's almost at a stage where it can be merged in the master branch now. So yeah, congratulations.
Thank you.
Any questions to Sebastian? Gauthier, Christian, I guess you might have some. Did you already see a use case where you could use this for your application already?
I think it looks pretty similar to our problem. So it's how many connections and links. Maybe one problem is that we haven't been that we haven't been on ROS-2 yet. So I think that's one more reason to go to ROS-2. Yeah, I think that we will do this in the next time, since we also were a little bit of waiting for drivers and ROS-2 control coming up and MoveIt2 coming up and everything.
Yeah, I think the UR5 driver was released last month or in March. So that was one big problem with ROS2, this kind of chicken egg problem. So a lot of people were talking that they don't port the library because there isn't any hardware yet, and the hardware guys without any libraries, we don't port the drivers. But the UR5 driver should be available right now. And yeah, when I saw your presentation, I was thinking that maybe this this architecture could be used kind of like in stage 3 and 4. So this to kind of plan the motion and then adapt it to the problem locally.
Yeah, I think so too, because currently our two, like this online toolchain and more the offline toolchain, are at the moment quite independent in our situation. So we can either have the offline programming environment and plan the motion and maybe optimize the path or avoid collisions from the simulation part. And on the other hand, we have the online toolchain where we detect the weld seam in an online manner and plan the welding path online during welding, but both parts are not so much connected yet. So I think that could be a great tool to do this. Maybe one question, which I'm actually, I think Gauthier is more the expert in path planning, but how would you, for example, rate a planner like this Pilz industrial motion planner? Because on the one hand, it's more like it's kind of deterministic, but it's, I mean, it's not maybe not that global as for avoiding collisions.
I think you could also use it as a local planner. So I think the border between the two types of planners is very blurry. So there are definitely some planners that could be used either as global planner or as local planner, depending on the scenario. And I think the main difference is the different planning speed. And so, for example, the global planner isn't intended to be run, for example, at 100 Hertz, but the local planner is. So that as long as your planner is capable to solve local motion planning problem with a frequency of, for example, 100 Hertz, it could be utilized as a local planner.
No, okay.
So Sebastian, do you already see that as probably one of the future works, as in which planners are more suitable for global and which planners are suitable for local planners, or some kind of benchmarking in that direction probably?
Sorry, was that a question or?
Yeah.
Yeah, I think so. I think all planners currently available for MoveIt could definitely be used as global planners, and I think that especially the planners that are used to optimize the trajectory are fit as a local planner. So, for example, thread job could be used as a local planner, but I'm not sure. I think there's a blog post on that PickNik. I haven't mentioned that, but when we merged the architecture into the main branch, we have a white paper I've written that we plan to publish by then, and there's also a more detailed kind of list which currently available planners are fitted for which use case.
Okay.
But I think especially there aren't many local planners dedicated as local planners available yet. So this is definitely one angle where I think more sophisticated. As I wrote in this slide, there we definitely need to add more planning algorithms than they're available currently.
I have an additional question, if I may.
Yeah.
What kind of what map representation are these planners using? Are both sharing the same map representation with boxes or distance field? What kind of?
So first of all, the global and local planner work completely independent from each other, and both components have this so-called it's a MoveIt specific thing, this planning scene monitor. So in MoveIt, this planning scene monitor is kind of a wrapper which unifies data from different sensor sources into a unified planning scene, which can then be used by for example this architecture. So both the global planner and the local planner have this planning scene monitor and receive completely independent from each other the current planning scene.
Yeah,
and,
but depending on the planner, you would need a representation of the environment, for example, for collision avoidance. No, for example, for chomp, you would need some distance field to construct this distance field out of the environment. No, but for the sampling-based planner, maybe you need a different representation. Or this is a play that is always tricky, no, because sometimes it's expensive to build the distance field, and
I have to admit that that's not part of my expertise. So it's kind of a different abstraction in MoveIt. So at this point of kind of the whole setup environment, I just received this planning scene independent from its sources. And the moment, for example, I don't use different sensor sources, I don't have this data available, and then the planner cannot utilize it, and probably will kind of give me an invalid solution because we don't have the whole picture of the actual planning scene.
Okay.
I would recommend you to take a look at the MoveIt tutorials. There, it is more detailed explained which kind of sensor sources you can use to include different data and make it available for the planner.
Yeah, sure. If you work with the abstraction of the scene, then I can just read it. Okay, then thank you very much.
Sorry.
All right. Any more questions to Sebastian, Christian, Gauthier? All right. Seems not to be the case. So I thank again all of you to present today your amazing work, what you have done in the last few months, and also for the audience as well.